I'm going to talk about architecture matters. And the dual meaning of that title is by design. So the task that we want to achieve is to build intelligent systems that work in the real world. And we're really, and the ambition of this workshop is trying to push that forward and saying, well, current techniques that we have may give us incremental improvements, but we have some reason to believe that they may not get us where we want to go, or at least in the best case, they're maybe slower than we'd really like. So that's an argument that I would like to make here in this talk, and I'll show you an example of what I'm talking about in videos that we have produced earlier this year in the Humanist Project, and then we will go into the final session of discussing the challenges. So these systems should be able to learn a host of vastly different tasks. I don't think there is currently any AI system that really this is true for, at least not in the commonsensical meanings of these words. Adapt to vastly new circumstances, that certainly isn't true. Or actively acquire new knowledge for the above as needed. I really don't think this exists. And if you do think so, we can discuss it afterwards. I'd like to hear some examples, but I'll guarantee you that that's because you are interpreting these words in a different way. I'm using this very much as the man on the street. So just a couple of things to start out. Intelligence is for the real world. Intelligent systems need to perceive, estimate, plan, predict, infer. The longer this list of capabilities of the system, ideally the smarter it is. But that depends on architecture, and that's why I'm talking about architecture. Another thing that keeps being forgotten is that natural intelligence is marched to an external clock. That's what we call the real world. And the phenomena that inspired us to actually even think about such a thing as an artificially intelligent system, natural intelligences, show us that there really are no intelligences in known existence that don't operate in real time. And I think Pei put it very nicely last week in his talk, or actually it was earlier this week in his talk that he gave here at the RU, where he said that basically, if you assume any such thing as infinite time or infinite resources or something vastly beyond practical means, then you don't need intelligence. So by definition, you've excluded the very thing you're studying. I just want to hammer that point home. So complex systems architectures are really a prerequisite for intelligence. There's no way we can achieve that long list of things if we don't have a complex, powerful architecture. And I think that this architecture does not exist yet. So intelligence implies a complex system, and a well-known feature of complex systems is that we will be able to identify a high number of processes with complex interdependencies, tight and loose couplings, rich and simple couplings, etc. And the operation of smaller parts are tightly integrated with the operation of larger parts to the extent where sometimes you really can't tear them apart. You have to study them as a unit. So here's another list. These interactions that I'm talking about, these are interactions between goals, perceptions, attentions, ideas, introspection, etc. We've covered a lot of these in the talks so far. And I just want to also emphasize this, that if we want a system where with these features and where they operate in a sensible way, our system architecture has to be comprehensive, and it must address a host of different design problems. Otherwise, we just build cartoons and we work on toy problems. So we really have to build more complex systems. How do we do that? Well, the typical way is divide and conquer. The scientific method. Isolate functions, modularize. And then work on one module at a time. And then add them together like Legos. By the way, there is no such noun as Lego. A Lego doesn't exist, but we use it. I learned that when I was working at Lego. They really don't like it, for some reason. What have we been doing in that sense? Well, we've been doing manual construction of systems by and large, and our modules are pretty gross compared to the big compared to the architecture. So it's a gross architectural approach. I like to, put this meme out there: the programmer as construction worker. You take each brick and you put the mortar and you put the next brick and so on. So construction by hand is the ultimate method, and we've seen this in it permeates our culture. It's everywhere. It's in fiction. The Frankenstein's monster's head was bolted on by hand, and in light of what we're talking about here, it becomes fairly obvious why such an approach won't work for example, for life. And I dare to argue that it's also not possible for intelligence. But we do have some very good examples of how strong or how powerful modular construction is, and this is an example I used to use in talks that I gave 10 years ago or so. You may have heard of the soccer team, football team, Crystal Palace. Well, it was named after this building that was built in 1851. It was a huge iron Goliath. It had a lot of materials. It was the largest physical structure ever. And it was built in only 17 weeks. And then it was moved to a completely new location in 1854. And, to top it off, Paxton was not an architect. He was a gardener. How could he do that? Well, all of the things that he brought to bear were modules, and then they were just bolted together. So, in fact, I would say when you build big systems, you really are forced to do manual construction. And we have a couple of more facts here about Crystal Palace, just to hammer this point home. I mean, when you see something like this, you go, oh yeah, of course we're going to have to build modularly. I mean, otherwise, how are we ever going to get there? So that's Crystal Palace. Of course, the current, good question, I have no idea. The current robots are, of course, built exactly the same way. And it's all based on this assumption that you can, you build modularly and then you just put things together, and eventually you will have a very large, big system that works. It works the way you want it to. So, so modular construction is tried and tested, but it's based on some prior assumptions, and I wanted to go over a couple of these that I used to believe or hope for, let's say, and I really don't think hold anymore. So I imagine that you could, if you had a few hundred or a few thousands of these modules that were all built by hand, if you had a good picture in mind of how they would connect together, you would essentially end up with a reasonably smart AI system that maybe could come halfway towards examples of human intelligence, or even further, or at least outsmart a dog, and that's already pretty good. And then the system, if necessary, would just do a little bit of auto tuning. It would reach in here and there, and it would tune parameters and so on. And maybe, in the worst case scenario, it would actually be able to. It would have a factory, so it could build a few of these modules automatically. But by and large, still the largest percentage, 95% of the architecture would still be handcrafted modules. So if we think about that, and we think about the complexities that we have to reach, and the long list of features that I listed before there, where you have all sorts of things interacting in very complex ways. The massive complex dependencies of all these features really prevent automatic construction of new modules. It really prevents reasonably automated routing of complex data. It becomes very top-heavy, and I've actually tried some of these myself over several years of work. So I would say the modular construction idea is essentially not going to work if you want the kinds of intelligences that I'm hoping to see before I hit the grave. So I would say, by and large, divide and conquer fails, at least in its most obvious form. Another line of reasoning would lead us to the same point. If you think about the sort of things that have to be system-wide in a generally smart intelligent system. You have temporal grounding, it's everywhere in the system. You have system-wide learning, and you have system-wide attention. It's very interesting. We humans are able to direct the attention of our mental apparatus to incredibly different levels of both abstraction and detail and time. And we can do that very quickly. It's only when you have really trained, sort of like the skydiving example, or examples like it where you have really thoroughly trained, you have something called negative transfer training, where you have, in fact, you've trained in one context too much for another context, so it actually negatively impacts you in learning the new context. This is, for example, if you are a very good tennis player and then you're asked to be also a very good racquetball player. This is, in fact, a known phenomenon. So anyway, you have learning across the whole system. You have this ability to direct attention to things and identify which things should be sensible to pay attention to for the learning you want to achieve, etc. And you have a lot of transversal skills in the mind. So in fact, I think AGIs would have to have system-wide support for such transversal functions. And eventually you end up with this, in this state, which is essentially intelligence is really almost the same thing as the architecture. The architecture is the intelligence. I mean, they are inseparable in some very important way. So it calls for an holistic approach. And there are heterogeneous components, a large amount of components and subcomponents and functions, and the connections are massive and messy. They're so messy that you really shouldn't even start thinking about doing this in the... It seems actually, when you go through this exercise, fairly hopeless. Although you'll see when we come to the challenges, I still haven't quite, locked that away in a drawer somewhere. It's still hovering there, the question of manual construction. But I really think you end up with at least this in this situation where you really want and need to build big systems, big architectures. And for that, and for the transversal skills, you end up with a conclusion that's really depressing. Because present software methodologies is really just all we have. For a while anyway. So that's why I think we really need to turn our attention to constructivist methodologies where we get the machine to help in the construction and management. So what kinds of architectures are we talking about here? Building. Architectures that change significantly at runtime as a cause of their experience, and they don't only activate and deactivate processes or control the flow or do parameter tuning as I was hoping, but they also create new processes and they architecturally rearrange the structures that are in fact learning. So we want architectures for AIs that operate in more than one real-world domains, and domain just interpreted in a sort of intuitive way. And in fact, this is repeating some of the things I've said earlier, that they need to be able to learn a vast number of complex tasks. And we really need new constructivist methods for this. I like to illustrate it with just a pictorial example here. You think about the complexity of a forest and all the processes going on and all of the sort of auto management here. And you think, okay, we're going to do this with tools. And we have a hammer. That is the ratio. Even if you go to this level, like, okay, it's not just a hammer. We have a whole set of tools. It's all just manual tools. You have to grab them by hand. Think about who's going to put up all the straws in that moss, I wonder. And I think this is the kind of ratio we're talking about. We know this from elsewhere. So what we need are self-construction principles, where the systems are growing to a ratio of 1 to 1,000,000 possibly of hand-coded to automatically generated code. And the modules must be small enough to allow for a lot of high degree of flexibility and transfer and reuse, not the big chunky, clunky modules that we're doing in software systems today. In the HumanOps project, we believe we are on a path towards that goal, and that we have achieved some very interesting results already. And I want to show you a couple of videos so that you don't think I'm just philosophizing here. But we do support some set of transversal skills, although there's still a lot of work to be done to really prove it to ourselves and to others that this can scale. We have what I call peewee granularity functions or programs in the system as the building blocks. These are more like grains of sand rather than bricks relative to a house. And before I show you the videos, I just want to thank Eric, Pei, and Krap for their excellent suggestions on all of these slides. So what you see in this video is a prototype 0. I'm sorry about the clipping. It won't matter for what you need to pay attention to. What you'll see here is an interview conducted in cyberspace where you have two avatars. One is controlled, both are controlled by a human interacting with the other human via their avatar. So one person has a screen in front of them, they see the avatar of the other person, and that is mirrored. There's a microphone and some tracking devices on their hands, and they can point to objects on a virtual table that sits in front of them. And so this is the situation. So you have on the left hand is what the person controlling the avatar on the right hand sees, and vice versa.
A red sphere there. Thank you. Take the sphere and put it there. Thank you.
So in this scenario, so the humans interact like this for maybe 12, 15, 20 or so turns. And they move these objects around, refer to them in various ways, etc. Meanwhile, our HumanOps architecture is watching the interaction. The system is given a few models, about I think it's 6 models of acting in the real world, what the avatars can do, and so on. It's got a small vocabulary of 20 or 30 words and a small ontology of what objects are in the world. Otherwise, its perception is the geometry in the world. So all it sees is essentially these tags on objects like ball, red, etc., and some coordinates and some geometries. So it has not been taught the art of dialogue, but it has been told that the goal of its existence should be to learn to act like one of these entities.
No, well, this is a consequence, in fact. The bootstrap code of that is, encompasses one single goal, is to hear thank you.
So yeah. So that's
in whichever
that's
way
the top level goal.
It could be implemented, and it has learned how to implement that.
Okay. Yeah. So it's a goal-driven system, and essentially the top-level goal is to hear "thank you." And if and it used we could delve into that would be another day, but we could delve into the architecture for how we achieve this. Suffice it to say that it contains the start of many of the principles that I went through in the slides earlier. So now the system has been watching the two people interact via these avatars for maybe 15 turns or so. That's about 1-2 minutes, something like that. And then we tell it to pretend that it's one of these people.
It observes this 3 times.
3 times. Oh, so it's smaller. Okay. So it's less than a minute even.
Put a blue cube there.
So the machine is controlling the blue avatar.
Thank you. Thank you. Take the cube. Put it there. Thank you.
And then we ask it to do the interview. So be on the other side.
But what does the system learn? All the motor movement and the understanding of the language and everything?
Yes.
Really?
By and large. So just to clarify, there was a good question over here. Some of the things that you might infer from seeing the video are actually not learned. So it looks like the system is actually learning natural language to its full extent. Well, clearly that's not the case, but it's learning to say, it's learning what to say and when to say it. Even though it has very limited, if any, understanding of the meaning, it can still operate after this very few examples, after seeing this very few examples. And here we switch it, and the machine
Put a red cube there.
is the interviewer. And it's the same. It's from the same set of sessions. It didn't have to get more sessions for the interviewer. It can do it after, either one of these after only a minute or so of examples.
Thank you.
Now the ratio of hand-coded programs to automatically created programs is starts out with 6 and ends up with 26. That's already a hint for us that we're actually on the right path here, and we really believe that this can scale. But we can't show you that because that's ongoing work. So let me launch into the challenges. Essentially, we've got two views. One is from the view that, we can still do hand coding and what someone called, I think it was Ricardo, top-down design. And the other says, okay, that is not going to work. It's going to be too complex. We need to automate some of these things. And the question is, how do we automate them? So if you can do either one of them, you can do both of them. That doesn't matter. You just as long as you work on some interesting aspects of these questions. In fact, the questions are the same, but they would have very different answers depending on whether you take one or two.
So your project is kind of Winograd's, only done with learning.
Yes, sorry?
It's like Winograd's thesis, basically. Is there a distinction? I mean,
No, it's not just syntactic manipulations. Because, and it's certainly...
well, Winograd was hand-coded. In what sense is Winograd merely syntactic manipulations? This took English instructions.
Well, he programs it. All
I know it's hand-coded, that's what I'm
And
saying.
the
You're adding learning to
The point
Winograd.
here understand is that it just finds this automatically. These
Yeah, I
responses.
understand.
Yes, yes.
Yeah, you know, it's learned. It's not.
Yeah.
That's what was wrong with. I mean, I like Winograd's thesis. I'm not running it down at all.
It's also Winograd's work in,
And I like
in
that, and he needs learning.
in those kinds of systems. They are kind of event-driven. So you input something and then it produces. So it's very much sort of a function, you know. It doesn't do anything unless you put something into it. But here the system is extracting goals and that's what's driving it. So it's a much more general system. So you can tell this system to get its goals from anywhere. You can add it by hand, or you can tell it, here's how you look for goals, or, you know, etc.
What I'm worried about is if you do this holistically, how can you ever verify in some feasible way that it works the way you want?
That's a valid question, but unfortunately we don't
For
have
me,
time
that's
for
the
it.
beginning. I'm also from more or less the Dijkstra school of computer science. Not only make a program and then thinking about how to verify it, but think of verification together with program.
We've kind of covered that in response to Ricardo's talk, so I'd rather not go into that.
Maybe verification as in the traditional sense is just not possible. Maybe to take a more empirical stance.
What in the hell could be?
Well, it's just as with us as well, as a mother does with her baby. It does it, and it says, no, 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 and then it does it again, no, 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 and then it does it right, this kind of thing. It's not like computer science, traditionally.
Yeah, but this is very simple behavior. How can you ever punish the system? It is very difficult.
Well,
One answer lies in the fact that, well actually there's a two-part answer that's very interesting, so I guess I have to answer that. One is that in order to answer it fully, because these are complex systems, they're designed for complex environments where you can't predict everything, you cannot verify anything except in its environment. So Bas is right, it becomes an empirical thing. But in our system, and the others, that's another answer, although the first one is still valid. In our system, the code is very explicit and simple, and so you can inspect it, in fact. It's not like a neural net. This is not like a giant neural net box where it takes 20 engineers 20 years to untangle the mess. So,
yeah, this would be my main question. What is the underlying architecture for that? So are these little modules apparently agents or something? And how is the actual computation?
that's exactly why we have a dinner tonight. Make sure to sit next to Eric.
Without the wine.
Soup.
Oh, I see.
That's funny because I never heard that, except when Eric and I were talking
Yeah, but
5 years ago, and I first and he explained to me what he wanted to do, and I said, that sounds like soup to me.
Yeah, it's a model that was proposed, I don't know, 10, 15 years ago.
Yeah.
And which I know it because in film proving you could do the same.
Yeah.
The clauses are not executed with resolution, but this clause finds another mail that and so it builds long chains all of a sudden.
And that's exactly what we have. Although not in this system, it's so small. And the example is, it hasn't been really real. Its full scale hasn't been realized But we really think that it can get there because we designed it with that in mind.
You need millions or billions of little strings.
And in fact, it's very much, I mean, this came also, this concept was not unfamiliar to me because I worked a lot on blackboard systems. And it is kind of the same thing, but the ratio is vastly different. You know, because when you start calling it soup, when it starts to feel like soup. And the blackboard, when the size relationship of the memory space to the, you know, the statements is like that. So soup. It's like the ratio of the size of the system to the meaningful modules that you work with.
I think Ricardo is waiting
Oh, sorry.
for a long time.
My question is a fundamental question regarding fundamentals. If constructivist methodologies are going to produce systems, they are going to be software, I imagine. What prevents us, that we are clever, to write that by hand? I mean, what is the fundamental difference? What is the magic that comes from constructivist that makes it impossible for us to write the same code by hand?
It's in some sense a practical issue. It's the same answer as if someone came to me and said, we want a forest. Can you build trees and glue on all the fir trees? And I'd say, no, I won't live that long. It's essentially the same answer. So I go out and plant a seed, and it's
Just compare not to a forest, because obviously a forest is a biological entity that we are not building. But compare, for example, with internet, the topology, the structure, the complexity, all the things that you have said there about systems that are not constructible can be said about internet. And it is fully modular, and it's being built. What prevents us?
That's a nice analogy.
What prevents us to have the same kind of thing?
Yeah, I see Eric has an answer. Let me just say very quickly that the number of heterogeneous components in the internet is vastly less than in the systems that we are envisioning, in my opinion. But I admit it's an empirical question. It's a hypothesis.
My answer to your question is the following. In the case of the internet, the engineers have been there constructing it all the time. What we target is you start and the engineer dies, or is not on Mars anymore.
But in the case of internet, is the case. Engineers are just appearing in the media. They are not doing anything more. It's people around there doing things. So it's a kind of soup that is
but the internet isn't intelligent and it doesn't act like a single entity.
I know. I'm not saying that internet is Skynet.
I know. But that's the difference. That is the difference.
Regarding the complexity.
I work with AI people who say, well, the internet may actually achieve consciousness one day.
No, I'm not saying that.
No, I know.
What I say is regarding the complexity and the distribution and the level of details that are there that really...
Yeah, there's a fundamental difference in the fact, because of the fact that the system has to act as a single entity, and it has to be able to obtain a top-level goal, or a set of them, and that's very, very different. And they have to be dynamic.
Remember my question, please. Yes. Why we can't write the code?
And as I said, it's a practical...
The code is going to exist. Why we cannot do that?
Why can't we represent the youth?
I think we can't articulate it better than not writing it.
Oops, we're breaking off into... Eric, do you want to say...
No, I didn't say that the reason is that the code is going to work in the future, and we cannot anticipate the conditions of operation to really write the code for that moment, in that conditions, in that context.
That's one reason.
But what happens if we are clever enough to do that?
Yeah.
So if we are clever enough to analyze the circumstances, to analyze the context, to decide...
That's what I'm saying, we're not clever enough. I've waited long enough to see a proof of that, and I don't think that's true. So.
I mean, maybe there's two questions, and you're answering two at the same time, really, with this approach. I mean, on one hand, you're saying that the current software development methodologies are not good enough to do these complex systems. On the other hand, you're saying also, well, we need an automated method. That will do it correctly. We'll find the correct method.
He's saying also that we are not clever enough.
Yeah, so there's an in-between question, which is, are the humans going to be able to produce a better software development methodology for other humans to build complex systems, not for computers? So maybe there's an intermediary step or an intermediary question that some people are pursuing. I mean, people that are looking into programming languages and so on, or software development methodologies. So, I mean, that will probably evolve, but this will evolve, and now it's a bit of a question, who's going to get it first, maybe. It's something really cool.
I think it's interesting because one of the conclusions on Ricardo's challenge yesterday was that we will probably need a mixture of constructionists and constructivists. So I think that the research on software engineering and methodology is of key importance, whether constructivist or not. We need it in any case. And if constructivist eventually makes sense, it will most likely benefit greatly from those as well. So those should be handled in parallel.
Yeah, that makes sense.
Yeah. And again, it's a practical issue. I haven't seen the kinds of funding that I believe will be necessary to do AGI into reasonable level with constructionist methods. Or I should say it's the same thing, with the methodologies that we use almost every day in computer science. But also, I think even if it was possible, it would take very long. And even then, if we get there, probably there would be cases like Mars where you really want the other thing. So we could postpone it forever. But I'm really answering the question about methodology for AGIs. I'm not answering questions about intermediate stages like, well, I have a partial problem that I need to solve here with how internet traffic is routed. So I need a semi-smart or adaptive system to, compared to, let's say, a squirrel. It's a quarter squirrel smart. That's what I need to really adapt to this routing. That's not what I'm addressing. So I honestly haven't really answered, in my mind, the question whether what we're doing is relevant for other lesser or let's say lower level goals in terms of ambition, in terms of autonomy and smarts.
Yeah, I have a comment on your conjecture that there's no way that there exists no elegant, simple method to build a system with a lot of intelligence. So this was, you had a well-reasoned argument for this. One of them was that if there were, we would have found it by now. So I just wanted to comment that there's actually a formal proof of this conjecture.
But not a practical solution.
No, there's not a practical solution, but you don't have to state it as a conjecture. There's a guy, Shane Lang, who was a PhD student at ITSIA. I did not check the proof. I only recently found the paper, but he actually shows that if you assume finite time and resources, then he actually proved that there exists no simple, elegant algorithm that achieves high intelligence.
But I'm not talking about algorithms. I'm talking about architectures. And
yeah,
you
move. Same thing. Sorry.
You already moved beyond algorithms in the general definition of that term once you start talking about architectures. And I certainly don't think there's a single algorithm that can achieve it. And I'm happy to hear there's a proof.
Yeah.
But it doesn't really make a big difference. But how are we doing on time?
We're done.
We're done.
Yes.
Okay.
So really, thank you, speaker, actually.